Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to my channel M.Asif Math Corner. Today we will discuss about a very important theorem. Positive divisors of cyclic group of order n give us unique subgroups of G. It means that for example G has order 6, then 2 divide 6, 3 divide 6, every divisor give the unique subgroup. So let's start. We have a theorem. Let G be a cyclic group of order n, means n elements are there in the G, generated by A. A is the generator of G. Then for each positive divisor D of n, divisor D of n, there is a unique subgroup of G. It means that, for example, order of G. For example, order of G is 6. Order of G is 6. For example, D is equal to 2. Then 2 divided 6 give us 3. Here 6, n is 6 here, and D is equal to 2. So every divisor give us, it means that 3 means that it give us a unique subgroup of order 3. G is a cyclic group which is generated by A, and A raised to power n is equal to identity. It means that G has order n, G has an element, because the power of A equal to total number of elements give us identity. So let's come to the proof. Let G be the positive divisor of n. Keep in mind 6 is n. 6 are the elements of G, and let's suppose any divisor D 2 divides it, which give us 3. So then there is an integer q. Q is 3 here, such that n is equal to qd, and it means that 6 is equal to 3 multiplied by 2. Just compare this general example and this special particular example. So 6 is equal to 3 multiplied by 2. It means that 6 is n here, and 3 is q, and d is 3. Let take B. B is the element of the subgroup, which is equal to A raised to power q, because A is the generator of G, all the elements of G generated by A, so its subgroups elements are also the powers of A generated by A. So if B is equal to A raised to power q, take raised to power D on both sides, B raised to power D, here A raised to power qd, and we define that qd is equal to n. So A raised to power n and A raised to power n give us identity, because there are n elements in G, and the number of whole elements give us the identity. So B raised to power D is equal to identity. It means that H is generated by B. H is generated by B, where B and elements of H. This statement tells us that H is generated by B and elements of H are D. For example, 3, 4, 5, etc. Because B raised to power D gave us identity, is the required subgroup. Now we will check that either H is unique or not. For uniqueness, to see that H is unique, suppose that K is another subgroup of G of order D. H has the order D, and we suppose that there is an other subgroup K of order D as well. It means that the element of H are D, then the elements of K are also D. For example, elements of H are 3, then K is another subgroup which has elements 3. Then K is generated by the element C. H was generated by B. Here it tells us that C is the generator of K, where A raised to power K, C is equal to A raised to power K. And B was equal to A raised to power Q, and C is equal to A raised to power K, where K is the least such positive integer as K has order D. K has order D and K is the least positive integer. Let's see next. A raised to power QD, it's mean that A raised to power K give us C, and taking D on both sides into raised power, we get A raised to power QD is equal to C raised to power D, give us identity because KD is equal to N, which is the order of G. So KD is equal to N, and here K is equal to N by D, because D is multiplying here, on other side it will divide, and we know that when N divided by when divides D divides N, it gives us Q, as we discussed earlier. So B is equal to A raised to power Q, because A raised to power K, when we take these K and Q in powers of A, so A raised to power Q was equal to B, and A raised to power K we discussed in this other example, that is equal to C. It's mean that here we proved that B and C are the same numbers. It's mean that K and H are same subgroups, not K is not an other subgroup, hence proved that H is unique. I hope you understood. Here the proof end, and thank you so much.